So good morning, everyone, and welcome again. Today we have a third webinar when I will explain you a bit more about the project and examples. If you know me a bit, my name is Marcin Ruta. I'm busy with power system engineering since the last 10 years and in overall 15 years in electrical engineering. So you can find a lot of details on my LinkedIn profile. We're not going to this too far. For today's webinar, I prepared plus minus 30 minutes presentation when I'll explain what we would like to explain today. Then we have a 15 minutes Q&A session, but in practice it can be longer because it's limited by Teams only. And yes, I will be recording this and I will upload this to the YouTube channel, and also you see this on LinkedIn. So let's go. For today's agenda, I prepared actually 2 steps because this is one long topic and I call it arc flash step by step. And I will try to show you an example of one and actually few projects that I combine into one presentation. So let's go with it. If you look on my LinkedIn, maybe on my articles, you will see this. I like to use this step-by-step example because I think it's very nice. But it gives you some idea what's happening when we talk about the arc flash. And this is, let's say, project example, how this will flow. So just to give you an explanation behind it, because we will talk about this in a bit of details. But as an overview, as we always start from the contact, then we go data collection, we go to the system modeling, we have to run the calculation. So say I have to do some report review and results review. Then I have to write the report, make the training, and then we have end, which is a follow-up and a lot of things. So this is in the few simple steps. It might be slightly different, but in practice, in most of my projects, it looks this way. So let's start. We have a contact. So as usual, we have to start somewhere, and this means that we have to prepare the offer, get to know what is the scope of work. And we discussed this in the previous webinar, what's important. So what we generally need the information about the electrical system. And the best way to do it is to have an electrical drawings. And I would say we can stop here. If you have a drawings, that's the best way to do it. For medium voltage, low voltage, depends what your site is. It doesn't really matter what is the form. It just has to be easy to read. It might be CAD form, it might be paper, photos, some equipment photos, sometimes Excel lists. Typically, we are looking for some information like how much transformers you have, amount of medium voltage switch gears, low voltage switch gears, panel boards, machines. Machines, I mean some kind of lines, machine lines, motors on low voltage, medium voltage, and we'll get into this in more details. Some renewable or UPS, battery energy storage systems and generators. What you see, I don't mention anything about the cables here and some other stuff which are not that important at the very beginning to prepare any first step. So just to give you an idea how this looks like from real projects actually. So if you have a drawings, for me it's very clear now if I have something like this. You don't see the details because I don't want to show too much details because the real project, real data. But I pick up that, for example, I see here protection size. I see also here the cable data, not too much information about the switchgear itself, but this gives me all I need to start. The same thing can be done in CAD, which is also the same and it's very good. So to prepare offer, make the scope of work, to have an idea how big the system is, this is perfect. But it might be also done in the photo. So if you don't have this, you have only paper form, you might scan it. Nowadays, I would say it's easier to make photos even by the smartphone. And if I can read this, that's all I need. And you know, the example here is part that I had one project when I had only Excel list. So it's not useful for modeling, but it's very useful if you have to prepare the scope of the work and start somewhere, or to guide the customer. The next step is we go to site. So we know now what's happening, what is the scope of work, what we expect to do, what customers expect us to do. So we have to go on site to collect all the data. And this is a very important step. I would say probably the most important step now, because the data collection is going on site, collecting the real data. And we also do a few things in when we do it. So that's me, just walking around. Probably if you see if I work, I also have balaclava, depends what we are doing. So just simple stuff that I carry. I wear the helmet because it's easier to wear it and then to drag it with you. Again, we collect the data. So I tried not to focus on details here because data collection is complicated stuff. But long story short, we collect the information about the drawings. Sometimes you have a drawings inside that you didn't receive earlier. So I just enter substation and I see the drawing somewhere on the walls and just make a very good picture of it so I can read everything here. I generally do a lot of pictures, a lot of photos. And so this is the overview of the switchgear, some panel board inside, fuses. So if I look for the data of fuses, this is the best way because I have everything here. And this can go on and go on and go on. There's hundreds of the photos like this. So normally I wrap up everything in some kind of Excel form. Because last year I started to generally work with digital forms, so I don't fill in things on paper, but sometimes you just have to make your note on paper. It's easier when you are in field, especially when it's cold outside and there's nothing, nothing is working. So I know that for you it's probably hard to see here, but there's a lot of information I need, like the photo of the feeder, some reference to it, cable type, length, the feeder name, the dimensions, which is the new things in IEEE 1584, overview of the feeder that is in the final circuit, some risk and IP covers. This is something specific that I will explain in a minute. Just give me some idea where I have to look for some issues, some comments, and then the reference. And then you see a lot of photos behind it, and I have to identify it somehow. And if I have it done this way, I even can give it to the customer later. And if we have some issues, we can work with this. So this is very easy to work with if there is something missing. Like here you see there was a reserve, but it was not fully clear what it is. So I like to work with colors, as you see. One part of the data collection is something which I call visual inspection. So because I will go probably to 80% of panels on site, sometimes all of them, and we open them, I will open them, have a look inside. This is not something like thermal infrared inspection or something like this, but I generally look for some non-conformities from shock hazard point of view and arc flash point of view. And I see a lot of strange things sometimes. So in practice, it's very easy for me at the end to prepare some kind of action list and report. This is physically report. When I check, okay, I've been an RN2 panel. I found there was some cable channel, there was some missing IP2X covers. So generally covers that will limit the shock hazard approach. And this is associated risk by me that's what is increased. The proposed action will be add covers, and then the risk that I will estimate is high or low or medium. And this list usually it's longer than this, but depends on the project, of course. It goes in some kind of overview like this. So this is the report, first page, but the whole report goes. I keep it simple, so it's very one page of what I did overview. This is also going in Excel list. So you get an Excel, but you have it in the report, then the list that I showed you before, and then the reference photos. So you can actually see for each photo, each list, each point, you can see the photo, what was the problem. Probably you can see from here there was some covers missing, and here are the covers, and there are no covers. So kind of easy things to spot. And as far as I have a feedback from customers, they actually like it because it's giving them the easy to solve stuff, I would say, and this is increasing safety a lot. The next step, once we come back from site and I have all the data, or sometimes 90-95% of the data I can already start, we create a model. So I have to create a digital model of your electrical system in order to do anything else. This is actually called now digital twin model because we would like to replicate your electrical system in the software. And as I said, data collection is a critical point because what goes in goes out. So if I have a rubbish data, then the results also will be not very useful or not, we cannot trust them. So what we need to include, because one thing is the data that we collected, but we also look on the operation scenarios. So when we create the model, we look on the what is the normal mode operation. So minimum, maximum, sometimes there is a UPS mode operation where the UPS itself can work in data conversion mode. It can work with the static bypass, manual bypass. Sometimes they call it echo mode also. You might have generator on site, which will work in island mode, maybe synchronized with the grid. So all of those are operating scenarios. There's also configuration, depends now how you call it, because you might have clutch or sectionalizer, bus sectionizer, which will be a tie breaker, which is open or close, maybe. Depends what is allowed in the operation and how likely it is that it will work like this. Maybe you have UPS with utility and generator together, min-max motor contribution, which will be where the motors are on and off. So all of this we have to include in our digital twin model. And to give you an idea what we talk about, and this is just example, plain example from ETAP, because it's hard to see, but that was the very one that I thought I can show you. So if you create the model, this more or less the concept is, we'll just put all the transformers, cables, breakers, switch gears, utility, everything else, what we collected. And we have to fill in all the informations. This is generally a topic for big training, not for the 30 minutes webinar, but I can show you that from the last project, and this is from the real project actually, that I had a lot of scenarios for Arcflash, as you can see, because there was multiple, partly because of the UPS. There was maximum, minimum configurations and multiple configurations. And also because of the UPS operation, we look on the minimum, maximum with the UPS in static and manual bypass mode. So we generally look for the worst case situation, not the min-max, but the worst case. And you might look on the configuration status. So this is from ETAP, some configuration, so you can actually see what's happening. The same thing you can do in SKM. Both softwares are used, but there are more softwares like this. So you might have, this is not very easy to see, so sometimes I just split things in small pieces. So it's easier to print this and see the details, because the model itself, the working model is much bigger. And even if you fit it on A3 or A1 or A2, it's sometimes hard to use it. So just very roughly to show you what's happening. The next step, once we have the proper model, is to go with the calculations. So calculations means short circuit study, selective. We discussed this in the previous webinar. Short circuit study, selectivity study, equipment evaluation. So based on the short circuit study, we try to look for the issues. Shock hazard assessment, just to identify what is the proper distances for specific voltage and the glove class, minimum thing, and Arcflash analysis. So in order to do this, we have to look through short circuit analysis, as I said. So we look for the multiple scenarios that we modeled before. We run multiple configurations and multiple operation modes. Also, motor contribution makes a difference. So if you have multiple motors that are not VFD or variable frequency drive operated, it will make a difference. So if you have anything which is DOL, direct online, or star triangle connection, delta star, sorry, then all of this makes a difference for the short circuit. And the changes in the short circuit makes the difference for us. So we try to look for the worst case situation, in this case maximum, because we look for the equipment evaluation, and then we run equipment evaluation, and I will show you what this is. So the most important thing for us is to pay attention for the short circuit data. Things like breakers models with the proper rating. And I had a project recently where, because on the breaker, the rating depends on the voltage level. Is it 220, 230, 415, 440, 690, and so on. And we had a project which was designed for 415 volts, and the rating of some breakers were 50 kiloamps. But because they were operating at 420, a little bit more because of the voltage drop, in practice for me it means, okay, the rating was not 50 kiloamps anymore, but the rating was, the next step was 440 volts, and it was 42 kiloamps. And then there was a lot of issues, I'll show you, a lot of issues with the short circuit rating of the breakers, just because of this. So again, we look on the switch gears. Typically, it's not the big issues with the big panels, but sometimes it happens. And the most critical for us will be proper transformer data and cable data. So we try to not to make too much assumptions around the transformer. Sorry. Simple example. So if you work, for example, in SKM, you can show partial results on the single line diagram on the model. Just to give you, like, for the one of the end feeders, you might see it's 13.6 and 23.3 kiloamps. But this is only a small part of the results. It's useful for me when I work on it because I can directly see where the problems are. But the better, if you would like to have a detail, there is always some results and the reports which are very much detailed than this one. And this is actually what we are looking for. And it has some kind of pros because we can use this as a part of our design later. So you have all the short circuit current calculations done. If you would like to exchange something in the future, you already have it. So you can use it as a base for your assumptions on what-if studies. Example of the equipment evaluation. This is based on SKM, but I will show you example on EMEA also. I tried to work on this a bit, so I can actually, as you see, I like the colors. So you see that this is okay, but this one is not okay. Very easy to spot actually if you have a very long list, and also filter because I give the results in Excel. So I'll show you at the end. The problem was slightly above, so the equipment, because that was a small panel board, 10 kiloamps. So it actually doesn't have 10 kiloamps. The breaker inside has 10 kiloamps. And it was slightly above, so we have to verify the rating of the equipment. So that's the first thing to check. Okay, for the customer, please go and check the rating of the equipment, because maybe it's not a problem, maybe we did some mistake here. But if not, then we recommend to change the breaker to 15 kiloamps instead of 10. So that's the next step solution. If you look on the ETAP, it looks a little bit different, but you might see the overview across different scenarios. And you can see actually here, yes, the worst was probably scenario 1. And actually scenario 1 was maximum, which is logical. And you can now see what is over duty, what is not properly rated from the short circuit point of view. The next big step is selectivity analysis. It might be called also protection discrimination, protection study, multiple names. But in practice, we would like to check for any issues related with the protection settings of our protective devices or types. So we would like to verify behavior in all of those scenarios that we did, especially for the minimum short circuit currents, because that's the area where typically the problems are starting to happen when something is not detected. Important is to check low voltage to medium voltage selectivity. So for example, across the transformer, because there's a lot of, as far as I see, there's a lot of issues, and not probably because not every software will allow you to do it in the good way. Then I see a lot of issues on this level. I at least try to show you clearly what is the difference between existing situation and recommended situation. So if we provide some recommendations for improvements, it's good to show you side by side what's happening if you do it. We print out TCC, which is time current curve, which is a graphical way of showing you the settings of our overcurrent protective devices, which might have different settings. Depends on if this is a phase protection, ground protection, if you use something which is called ARMS, for example, or ARMS, energy arm, arc flash reduction, maintenance switch, or you might have some adaptive settings, different groups. So all of this we try to show. And you see there are more points here, because we would like to include for selectivity evaluation. Sometimes you do it, you check the selectivity between the main incomer and the biggest feeder. And the rule behind it is that if you check the biggest one, the smallest one also will be selected with the main one. It's not always true, because if you have a different type of devices like the fuse, breaker, or MCCB or MCB breaker, they have a different characteristics and it's not always the same. So at least I try to check all of them, at least all of them with example from the biggest in the group. But in most of my projects, I try to check 90-95% of the feeders, unless they are exactly the same. So the next step, important one, is to verify your model. Is it correct? Very often there are some issues. So I know that some of them are validated by the software providers, but still you can find some issues with it. So you have to check if there is no any issues with the model itself, because it will jeopardize all your work. If you do any assumptions, so you replace model of the breaker with something which is similar, again, check if this is the same, because some of the breakers, some of the fuses are generally the same. They have just different name because of they are used in ANSI or IC word. So you might do some assumptions with it, but be careful if you go too far. And as a rule of thumb, I try not to do more than 5-10% assumptions in the project at all. When we go to the UPS, which is very common now, in UPS you have to be careful if you look on the double conversion mode, because it will typically there will be specified fault true current that is going from UPS in to out in the double conversion mode. And look if this is one phase, three phase level given, because they will be different. And also look on the time, how long the UPS will sustain such fault, because it will make a difference for the arc flash calculation for sure, and also for the selectivity. If you have a multiple generators, which sometimes happen, and all parallel connections to same feeder, have a look, because there is a fault split and or course shift, and you will see this in it will affect your protection. CT saturation, so sometimes it's easy to spot if there is a problem. So if you see the short circuit current level and CT rating, you might, as a rule of thumb, see, okay, this is not correct, but then you can calculate it. So this is optional thing, and especially for any odd settings on medium voltage or transformer protection, common issues. So just to give you an idea how I do it and how this looks like. So this is a kind of extended small project that I did for some other webinar. And just to give you what I mean side by side. So if I work with select, you will not see too much details here, but I will show you an example later. So you see time current curve. This is a time current curve. And you see the settings from the medium voltage to low voltage feeder as here. And the other one is here. They are identical. Just this one was done to be selective and this one was not selective. And I try to highlight the difference here. So if you have a TCC with existing settings, and I give you like overall, yeah, this is not selective. And if I can improve it, so it can be selective or partially selective, then I also give you the comment why. So usually there is a bit more comments than here, like why it is selective, like for example, that this is not okay, this is not okay, and the fuses which are 160 and 160 will never be selective, for example. and some recommendation. This was actually given by one of my customers as a feedback that I can write recommendations as a side separately. So once we have done this, which would be existing situation, I review the results and provide improvements, which is this thing here. So an improvements is related with bigger topic because it's related with what we did in the visual inspection. Short circuit evaluation also has an influence into it. Selectivity for sure, and arc loss. So we try to do this, and then we provide the recommendation and come back with the second set of calculations. That was, for example, from one project when we look on the selectivity, and you see, okay, I cannot improve selectivity here, but what I could do, I could improve the arc flash. And I wrote it that, okay, we can provide recommendations, recommended settings, not because of selectivity, because I cannot do anything with this medium voltage fuse. It was done. Generally, it's okay from transformer protection point of view. Just is bad from selectivity point of view because this combination is not selective. And because it's from really project, I know there was also a relay upstream, which was also not selective with the rest. So what we did, as a low-cost solution, we look on the settings on the breaker to improve the arc flash only. We improve the selectivity, just to give you an idea. We can replace this fuse with relay. Aside if this is possible physically on site, because normally I look from the low cost to higher cost on the recommendations. But in practice, if this will be possible, we'll change the fuse to relay, make it more selective like this. So generally make it selective, improve the arc flash a bit. So we go from 9.2 to 6.5. It's not a big difference, but the focus was on the selectivity. And the bus side, because we adjust the breaker a bit, we went from 9.2 to 0.8, which is a big difference. But just an example on the selectivity level. Same thing, you can, if you go to the arc flash risk assessment, as I showed you before the model. So this is the working model in SKM. It's hard to spot things, so I zoom it in for you. So like here we have the problem that I show you 9.9 calories, which was on the line side and on the bus side, because that's because of the fuse, which is upstream. There was the feeder 13.6 that we didn't expect here to happen. And there were two other transformers which were 59 calories on the line side, which is a lot. So that was the one that I showed you that I changed the breakers a bit, but I cannot fix the line side because of the upstream fuse, which is fixed. You will very often see the arc flash results in form of table. So just to give you an idea, that's how it looks from SKM very often. I use the colors because the colors are not standard things. So I use the colors to highlight bring it on a bit. And this is the overview from the ETAP. So I also play with the colors again. So it's very easy to spot now what's happening. ETAP does it automatically, but I play with it myself so I can have the same colors. Just to give you an idea now how to improve, especially on this one project, how we improve one side. So that was one of the small, I can go back. So that was this feeder here. It was 13.6 and we can do something about it. It was rather easy. If you look at it, I know it looks a bit of a mess, but this blue thing is a medium voltage fuse, which is here. The red one is the main incomer. The green one is a feeder to this panel. And then we have an outgoing fuse. So this is generally not selective at all. This green feeder that is protecting this this panel. So this thing is here. It will never trip, most likely. So we have to improve it a bit. Because we have a bigger problem with the arc flash, and that's the reason behind it. So we can actually see here that this breaker will trip something like, technically something above 10 seconds. 12 seconds or something like this. So we can improve it to make it better. I did, at least what I propose on this, because we cannot improve selectivity here. So at least we can make it faster. So we changed a bit settings for the main incomer. we changed the settings as far as I could because it was fixed. So we changed the settings for the outgoing feeder. So they will be not selective, but at least they will be fast. And the big difference is that now they trip in something around 50 milliseconds. So we can have, instead of 13.6, we can have 0.8 calories. So that's the difference, but this is still not selective. This is not ideal situation. And my proposition was to, because there was some remote operating panels, they can use this instead. But there's a bit more behind it. So just to give you an idea, so that's again what I did with the selectivity. I do very similar way in the ArcFlash when I show you limited results instead of the big table, and you can see what's happening now, what we recommended, and you can see the changes. So you can see that here I cannot do anything because it's of the medium voltage fuse, which is fixed and we cannot change it, and we just recommend or to check recommendation for future exchange of fuse to relay. And if this will be possible, then we can play with this. Here you see there was something rise up, so I changed settings on the low voltage feeder in the transformer, which went up a bit. But this one we went down a lot from 13.6 to 0.7. This is a huge difference and huge improvement on safety. Once we have done this, we have to give the results and provide it in the easy to read form in form of report. So I try to combine the report in the specific way. At least I think it's easy to read. We will not go to all of this because it's time consuming, but I try to keep the report in general form with all the details that are needed to understand what's happening. So all the reports, conclusion and results from ArcFlash and selectivity are there. Everything else goes to attachments. So at least I think it's a good idea because they are very detailed. A lot of, instead of having this, for example, this has 40-50 pages instead of 500, which I believe is a good point to have. So all of the results from short circuit evaluation, graphic settings for existing situation, I try to split it in the appendix A and B, and let's say recommended situation and results for the recommended situation are in appendix B. Not everything is changing like short circuit data. Once we have done, so the reporting is done, we also have to provide the ArcFlash labels, and they have a multiple form. I can show you just examples from some of the projects I did, and they are mixed between ETAB and SKM actually. So very important part is that, for example, this went to US, so they have a little bit different colors. Technically, there are ISO colors for what we should do, but in practice, I didn't see it used. So I try to follow yellow colors, and sometimes I use red for results above 40 calories, but there is still word warning instead of danger. So for future, because I think it's not exactly correct, so for future, I will stay with yellow only and warning, because everything up to 100 or 140 calories, we still have PPE. So you can still protect yourself against it. So there is no reason to give the word danger above 40 calories, for example, because word danger means that we cannot work on something anymore. But this is ISO and ArcFlash results are not well related yet, at least. So that's from ArcFlash point of view. And there was one step that I didn't explain it here. There was also training and follow-up. So normally we do ArcFlash training at the end, sometimes at the very beginning, depends how the work is going on. And generally the ArcFlash training is the point where we explain and transfer the knowledge. It's good when I do it on the specific results, so I can actually focus on what's happening on site and show it in the real life. But if not, then we do at the end or at the beginning, doesn't matter. Just the idea behind is that people has to understand what's happening. And then is follow up 5 years. So I have some, what else can be done with this? So related topics with what we do now. We have to provide, at least I do, some kind of simplified guides and instructions So when I finished, I created some kind of very simple document which summarized how to read my report, how to read the results, how to read the labels, what are some kind of extract from NFPA 70 when it comes to the risk assessment for what you are doing. You should update your electrical safety plan. So once you have done the study, you have to update it, and with ArcFlash requirements, so kind of add-on. Consider maybe ArcFlash labels unification, so you don't see it before. So sometimes you can show the exact results on the labels, but it's a good idea to round up to the certain values which are all related with the NFPA table, like up to 1.2, up to 12 calories. So we can now kind of round up the results, so the labels will be kind of similar across the site, but at the end they will be more flexible. So they will, if something will change and it's still in the range, we don't have to change the label. So it has some advantages both ways, or sometimes there are some disadvantages of it. I try to simplify PPE selection for the customer. So what this means, I just provide them some kind of table in Excel where they can have pre-selected PPE for specific range of energy. So at least I think it makes it easier. When we finish, of course, we can do a lot of what-if studies. So everything which is not included as a beginning in the study, in the report, we have some follow-up discussion, report presentation. Then there are a lot of ideas from the customer side, and we can discuss it. And if they have idea like, okay, maybe we change the switchgear, we replace the protection, we have some, maybe we add ArcFlash detection. So we do something like what-if studies to find out what the influence will be on the system. You can always update your electrical drawings, I mean detailed. So what we do now, I prepare the model, I prepare some kind of electrical drawings already, and this can be extended by the customers to a lot of details. And future steps, I still struggle a bit if I have to include more details in the report itself or make it easier to read with attachments. For a moment, I go with the attachments because I think it's better, but some people would like to have everything with the big one report, which they can print like 500 or 1,000 pages. So biggest one I saw was 5,000 page report. Simplified PP selection with pre-selected PP sets. So I already started this, and I already have some kind of Excel file which I try to share with the customers as a help. Required PP on ArcFlash label, and this is something for me tricky because we can refer precisely what kind of PP we need on the label itself, but that on the other side the label will not be that flexible anymore. If you start to change things, you will have to start to change labels, and sometimes there are hundreds of labels. So we can also simplify modification and report updates for this 5 years review, which is the tricky part again. So for what I mean behind it is I'm looking for the simple way how to track the changes in the system. So if I receive it after 2 or 3 years from the customer, they can fill it in, not by hand somewhere, but in the easy way. So I can actually see and go through it and update the results. Simple pre-assessment checklist. So this is something new. They already started this year, recently, which will be, this pre-assessment will tell you what you are missing, what is missing in your, so do you have any ArcFlash, what's happening on your site? Very general. And ArcFlash compliance audit is something what I started last year, which will be a kind of gap analysis, which will tell you if you are missing something. So you already done your study, but you have some guess, so we talked about it last time, and you are going to check, I'm going to check, actually do some kind of audit, exactly ArcFlash compliance audit, which will, as it is, tell you if you are missing something and everything is okay. So that was all for today. Thank you that you stay with me. So the next webinars, so still we have a few more to do. And I plan for the next one, mitigation solutions. So the overview of the mitigation solutions, very simple, as far as I know and as far as I use, most common. Actually, the next 3 webinars will be about the mitigation, because one will be about the example on specific project I did. And the other one is also an example, but more on ArcFlash detection that we did on one of the sites. And the other one was how we fix it with the settings in more details. So you can always, look on the webinars newsletter I created on LinkedIn. I think I will just create the mailing list. So this will be much easier to sign in and receive the update on next webinars. Maybe it's the best way. So I still have to prepare it. So now we have time for Q&A session. And let me look if I can find something. So yes, I will share the video, so it will be on the YouTube, and just have a look on my newsletter or on my LinkedIn channel, but you will find it there. Does inspection visual include dimension, cubicle, MCC, switchgear? Because the new ArcFlash methodology calculation requires it. No. So as a part of data collection, I collect the size of the cubicles and the electrode configuration. So this is just normal data collection part. Visual inspection is something from, let's say, shock hazard point of view. So I cannot open now, but what I do, because when I collect the data, I open the panel, let's say, and I see that when I open the cover or I open the doors, I immediately, for example, can grab the bus bar, the main bus bar. So I have my PPE, but not everyone has it. And the good idea behind it is to put the plexiglass, put the covers, so you don't have this shock hazard risk. Because when you have a shock hazard risk, you immediately have also increased arc flash hazard risk, most of the time at least. So I put it on the list and say, okay, you have to put some IP2X covers here because it's missing. Or I see there is, for example, there are no covers on the breakers. So you can easily touch the lugs of the cables. That's what, for me, visual inspection means. So it's very, it's kind of non-conformities inspection from, let's say, mostly shock hazard point of view. But sometimes I see things like, almost cut cable that is touching itself between the phases and they are damaged. So I put a lot of those things on the list. Do you consider medium voltage switchgear internal arc classification, HG, IFLR, in your arc flash assessment for PPE? Yes, David, I included. So you don't see it here, but it will be in the next webinar. So internal arc classification for medium voltage switchgear is included. If we have it, for normal operation, you don't need any PPE, to be honest. But if you start to do something with, which is rare on the medium voltage system, but let's say if you would try to measure something on live, very unlikely, but let's say, then your internal arc classification doesn't work because you have to open covers, remove them. And so again, probably 99 on 100 medium voltage switchgears now are internal arc classified. And this has an influence on the arc flash calculation. So what I do, I check if their short circuit current and withstand time for internal arc classification is in range. So if this is 16 kiloamp 1 second, we check if we are in 60 kiloamp and 1 second, because it might be that you are 12 kiloamp, but the time on upstream is 1.2 seconds, which will mean that, yeah, no, it's not okay. So you have it, but it will not work most likely. The same you can have for the low voltage switchgears, which is, it's not called internal arc classification, but the arc flash resistance, I think, arc resistance. So the standard is updated now. And the problem on low voltage with the same story is a little bit different, because on low voltage, I would say probably 1 on 1000 switchgear would have arc rating. And the problem is that it's very easy to work on live, on low voltage systems. So very often if you open it, then you don't have this arc rating anymore. So you need to have your PPE to do something on live equipment. Does your model take into account the current limiting effect through the fuses? No, because it's officially forbidden by ISC 60909 to include this effect. So if you do short circuit calculation, you might include it, depends on software now you are using, but for the short circuit calculation, you cannot take this into account. So you have to run this as it is. If you have 35 kiloamps, 36 kiloamps, that's what it is. The next step is for evaluation, let's say, for selecting your equipment. you can take this into account. So you can check, okay, my fuse will limit the current to 10 kiloamp instead of 35. And you can select a little bit better or smaller MCB or MCCB, whatever you want. But as a rule of thumb, and that's what is actually very clearly written in IEC, that you cannot take this into account. You can take it later into account when you are selecting your equipment. And in most of the software, you can use it actually. You can include it. Let me look into the Q&A box because I told you to answer here. Okay. I think that's it. I don't know if you have any more questions. Feel free to ask. I'm waiting a bit. Yeah, as I see, the example was calculated according NFPA code. Is also a calculation according ISA possible? Yes, it is. So I have few projects in past that I did. What I can say that NFPA means NFPA 70E, which in practice means IEEE 1584 method, most of the time, I would say 99%. And ISA guide, which refers, this is just a document, but it refers DGUV 203077, which is a, let's say, method that exists mainly in Germany for box method test. So let's say NFPA, when you work with NFPA, I don't have this slide here, but NFPA works with ATPV values, so open arc PPE testing. So you can select based on this method, based on this calculation, you can select PPE tested according ATPV, LIM, and EBT50, which is in calories per square centimeters most of the time. And ISA guide refers to DGUV, which is box method test reference, which will allow you to select PPE based on box method test, which is class APC class 1, APC class 2, arc protection class 1, arc protection class 2. To be honest, it mainly exists in Germany because it was done by the DGUV, so German Institute, at least given. I had a project recently, three projects recently that I work with DGUV system, and because we do both DGUV and IEEE 1584, my conclusion from this was that DGUV is much more limited at the end, so it will give you much worse results at the end. And very often you see that something which you can work with an FPA, like 4 calories, 8 calories, and you can select your PPE up to 100 calories in Europe and 140 calories in US. It will give you, on the other side, in DGUV, you eventually run out on the APC class 2, so arc protection class 2, you'll be over it very, very fast. So eventually it will tell you in a lot of locations that you cannot work on live equipment, while using NFPA 70 you still can work because you have much better PPE, much better. There are also the same PPE, but they are tested in a different way. I technically prefer NFPA 70E because the ISA guide, the reference to GUV is theoretical model. So at least they didn't show the, at least yet I haven't seen any test results. So I would say 99% of my projects are NFPA 70, IEEE 1584, which can be used in IEC world also. What is the difference time recommended between two protection plot? 0.2 milliseconds, I think 200 milliseconds you mean. And there is a buff book, so former color books from IEEE, which you can find. And also we have NPAC book when you can look for the recommended time interval between two protective devices. Because there will be difference if you have a fuse to breaker, fuse to fuse, old electromechanical relay to new digital relay. But as a rule of thumb, you can keep 200 milliseconds. Sometimes it goes up to 300 milliseconds in practice, and sometimes it can go lower than 150 milliseconds. But as a rule of thumb, 200 milliseconds is a good approach. So if you are on the low margin, you always can check the manufacturer's data, because they sometimes specify